Example 11.2a says use Cramer's rule to solve each system. So our system is given to us. We have the first equation, x minus 2y is equal to 5, and the second equation, 5x minus y is equal to negative 2. So we're not going to do any elimination, substitution, although that might be a path that you would like to take. We're going to practice using Cramer's rule here. So I need to set up three matrices, matrix D, a matrix dx, and a matrix dy. Always start with matrix D. That is the coefficient matrix where the coefficients are coming directly from the first and second equation variables. So looking at the first equation, to fill in the first row, I would have coefficient of 1 and negative 2. Those are coming directly from the x and the y. Go to the second equation for the second row, and you will have 5 and negative 1 as the x and y coefficients there. Use matrix D to help you create matrix dx and dy. Matrix dx is supposed to look just like matrix D, except you're going to omit the x column. So you're just going to have negative 2, negative 1. Matrix dy is supposed to also look like D, except you're supposed to omit the y column. So we're just going to copy down the 1 and 5 for the x column. And then for each of the dx and dy, wherever you omitted a column, you are going to then replace it with the constants from the system. In this case, those would be 5 and negative 2. And that gives you all three of your matrices. Now you want to move on to the determinant calculation for these three matrices. Start with matrix D, because you want to make sure that the determinant of this is not 0. If it's 0, then you're going to stop Cramer's rule altogether, and you're going to start looking at your equations to determine if they are parallel or exactly the same, because it's not going to be an intersecting lines case. So that's where I want to start. Determinant calculation will start with D. That'll be 1 times negative 1 minus negative 2 times 5. That's negative 1 minus negative 10, which gives me the real number 9, which is not 0. So that means that we're in the clear on that. Let's proceed. Let's find the determinant that goes with dx. That'll be 5 times negative 1 minus negative 2 times negative 2. So that's going to be negative 5 minus 4, giving me the real number negative 9. And then finally the determinant for dy, 1 times negative 2 minus 5 times 5, negative 2 minus 25, giving me the real number negative 27. So with these three determinant calculations, I can now calculate x and y. X is supposed to be the determinant for dx divided by the determinant for d. That's a ratio. Determinant for dx we said was negative 9. Determinant for d is positive 9. And that ratio will simplify to be negative 1. Now normally when we find the first value of a variable, we have to do a back substitution step. Here you don't have to do that, although you could if you really wanted to. It's not necessary. What we can do now is just calculate y directly using the ratio determinant of dy divided by the determinant of d. So that would be negative 27 divided by positive 9, resulting in negative 3. So the x and the y should come together, giving you the proposed solution negative 1, negative 3. As I mentioned before, if you follow this process it should just spit out the answer without you having to do any additional elimination or substitution technique. With the additional elimination and substitution techniques, we always said the final step was to check. There's no exception here. We can check. We're going to take the values that we just came up with. I'm going to let x be equal to -1, y be equal to -3. Then I want to look at the first equation. X minus 2y equals 5, which is going to say -1 minus 2 times -3 is supposed to equal 5. So that would be -1 plus 6, and that's a true statement. 5 does equal 5. The second equation, do the same thing, just to verify. 5x minus y is supposed to equal -2, so that'll be 5 times -1 minus -3, and that will be -5 plus 3, resulting in the true statement -2 equals -2. So that verifies that the ordered pair really does work. Put it in a solution set, and I'll box it in as the final answer.